How's it going, everybody? So today we're going to be talking about systems of equations, but we're going to be talking about them in the sense that they're non-linear. Okay? So just be aware that these kind of systems have quadratics built in and an occasional linear line. And we're going to be once again re-looking at where these graphs will be intersecting, not necessarily x-intercepts. So let's go ahead and take a look at some variations that we could see. So some common ones could be something like this on a graph where you have your quadratic here, but then it crosses and hits at a single point. Now, if there's only one intersection, that means there's only one solution. Another example would be something where it crosses at more than one instance, and so you'll see two intersections, which is two solutions. So this would be one solution, two solutions. And then yes, another example where it crosses nowhere. The lines or the graphs will not intersect, and so this will cause us to see that there is no solution, okay? Not that there's no x-intercepts, but that there's no solution in terms of an intersection, okay? Now, let's take a look at an example of how we solve these types of systems of nonlinear equations in terms of substitution or elimination. So let's take a look at that. Here's the example. We're going to be using elimination on this. So the biggest thing to do is to make sure that you have a variable that is the same number but opposite sign. And the variable that you're always trying to eliminate, which is now even more convenient, because if you remember when we did 3-variable substitution or 3-variable elimination, you had to sit there and pick, all right, is it the x, is it the y, is it the z, like what am I doing? But here, it's very straightforward. You're always trying to eliminate the y. Always get rid of y. So here in this scenario, we see that the y is negative and we have a positive. So that's good for us because we want them to be the same number opposite sign. So if we were going to do elimination on this, we can go ahead and add them together, okay? And so we're going to go ahead and add all like terms. So this right here, 2 plus 2, this is 4x squared. Then the negative 8x minus the 16x, that's going to give us a negative 24x. And then the y's, yes, they zero out, so you have your 0y, so they're going to go away. And then negative 5 plus a negative 31 is a negative 36. So you're left with this right here after you get rid of the 0y. Now, what's nice about this is this actually closely resembles a quadratic function that we've seen before in the past. If we actually get everything to one side, meaning I could add the 36 on either side, I could get this to looking like maybe the AC method where I could then factor it because it's equal to 0. Now, by figuring out, by factoring it and figuring out what x values, okay, these guys are equal to, this is going to tell me where the x values of the intersections are, okay? Not where the x-intercepts are, but where the intersections are, okay? And I'll try to make more sense of that in a second. So let's go ahead and try to do the AC method on this because I see an A, B, and C value. But I think I could divide everything by a 4 to make my life a little bit easier. So let's divide everything by 4. And so now this is going to give me an x squared minus 6x, and then plus 9 is equal to 0. Now, if you're familiar with the AC method, you'll remember that we're doing a times c, which in this scenario is 9. And I got to think of multiples of 9 that would add up to a negative 6. And so right off the bat, what comes to my mind is negative 3 and negative 3, because when multiplied, that's a 9, but when added, it gives you negative 6. So this is going to work. So I have myself a x squared minus 3x minus 3x plus 9 is equal to 0. And I'm going to split this down the middle, okay? And I'm going to figure out on the left side what they have in common, and then that'll help me with the right side. So on the left side, I notice they only have an x in common, so I bring an x out. That's a like term, I factor out, and I'm left with x minus 3. Now the beauty of this method is always that what you end up with on the left side is, in terms of a factor, you will see it on the right hand side. So you'll get x minus 3 over here. But the term that goes in the front of the factor, you got to figure out what that is. Conveniently here, it looks like it is a negative 3, because if I do negative 3 times x, that gives me negative 3x. Then, likewise, if I do negative 3 times negative 3, that is a positive 9. So this checks out. So now let's get our factors. I've got my duplicates, my x minus 3's, and then the terms on the outside come together to be the next term, so x minus 3. Now looking at this right here, what we then typically do is we're going to go ahead and put these factors equal to 0. So I have x minus 3 equals 0, and then x minus 3 equals 0. So this in turn is going to mean x is going to equal 3 for both of them, okay? Now what this means to me is, since they ended up as just the same answer, I'm only going to have one solution, okay? Because just because I find two of the same doesn't mean there's two answers. This just means that I have one solution, okay? Now, x equals 3 is important, but what I need to then do is find a ordered pair. That's the whole goal. And the way you find that ordered pair is you plug this back into the original equation to find the y value, okay? So over here, I'm going to utilize one of the equations from the originals that I had, which was, let's use the top one, 2x squared minus 8x plus y is equal to negative 5. And if it's still unclear as to what I'm looking at this guy right here, okay? And so I went ahead and found that x was going to equal 3. So I'm going to plug 3 in for x to find my value of y. And so let's go ahead and do that. So I've got 2 times 3x squared, so 3 squared, my bad. 8 times 3, and then my negative 5. So now it's just a matter of solving for y. So 3 squared is 9. 9 times 2 is 18. Negative 8 times 3 is 24. And I'm one step closer. Now this right here is going to add up to a negative 6, because 18 minus 24 is negative 6. And then I'm going to add 6 to both sides, giving me a y is equal to 1. And so this right here is my value of y, okay, that goes with the x value. So my answer that I've been looking for, my intersection, my solution, okay, also known as the intersection, is going to be 3, 1. So if you were to look at this on a graph, that is where both of these quadratics are going to interact, is at 3, 1. And what you can also do is, to check your answer, you could plug this into like a Desmos graphing calculator and verify that it does work. So there are ways to make sure that your answer is correct. So the idea is, if you were to plug this into Desmos, at 3, 1, we should see the intersection where both of them shall meet. Now, I did mention that there was a substitution, right? And this is if you would prefer this over the other. It is not necessarily something that you have to do. Because remember, substitution and elimination find you the same thing. So say you had a 2x minus 3 is equal to y plus 5x squared. And then you had a 3x plus y is equal to negative 3. Now, the idea behind substitution is that you want to isolate the variable of interest and then plug that into the other equation. Now, to make more sense of that, is I want to get this value of y by himself. And in order to do that, I have to get rid of this 3x. The way we're going to do that is we're going to subtract him to the other side. So the way this would look, okay, for this whole thing right here, okay, I'm going to subtract 3x, and that's going to give me y is equal to negative 3x minus 3. So the idea is that I subtracted it, and I got this now, okay? Now, what's awesome is, since I know the value of y now, I can now plug it in over here into the second one. So this whole bit right here is going to go here, okay? And that's going to get rid of the y, kind of like how we did in elimination. The y ends up going away. Now, let me go ahead and write that all out for you. So you've got your 2x minus 3 is equal to, and maybe writing this in or highlighting it in red in a second will help too, plus 5x squared. So this piece of information is the same, okay? Now, let's go ahead and combine like terms. I noticed that I have some values over here to the left I could push to the right. So I could go ahead and subtract 2x, and that'll combine with this. And I could add 3, and that'll combine with this. So I'm left with 5x squared, because these go away, and a negative 5x. I forgot my squared. There we go. And then negative 3 plus 3, those will also simplify out, leaving me with purely just 5x squared minus 5x equals 0. Now, this right here is similar to instances where when the c value is 0, where you can actually just factor immediately what they have in common. And what I see right off the bat that they have in common is I see that these guys both have a 5 as well as an x. So I'm going to factor out a 5x. And so I have a 5x, and then an x minus 1 is left behind. So this is awesome because now I can immediately go ahead and start solving for the values of x where the intersections will be located. So I have 5x equals 0, and x minus 1 is equal to 0. So there's a step-by-step process, right? So as you can see, once you get rid of y, you then try to see how you can factor into your x values, or to your factors. Then to find the x values, you put those factors equal to 0, so that way you can then figure out how to then get the y value that goes with that x. So we're going to go ahead and do each one. So this is going to give me, when you divide by 5 on both sides, x will just equal 0. So that's one intersection. And then we're going to add 1 over here. And we have x is equal to 1. Okay? So looking at this right here, we're going to have 2 that we have to plug in. Now, what I always recommend is always choose the path of least resistance. Let's utilize the one that's easy to solve. And believe it or not, we have one that's easy to solve. This guy. This guy's already solved for y, so why not just use him in the grand scheme of things? So if I do y is equal to, and I'll do 0 first. So when x equals 0, negative 3 times 0 minus 3. So that'll give me 0 minus 3, so y equals negative 3. So I have an intersection at 0, comma, negative 3. So that's one of my answers, okay? But then what is the intersection when y, or when x equals 1? And so that's going to give me a y is equal to negative 3 times 1 minus 3. So I have myself a negative 3 minus 3, which is y equals negative 6. So the other solution that I have is 1 comma negative 6. And there you go. You finally have your 2 intersections. Remember, that's what these are, okay? These aren't x-intercept. Well, this one over here, this top one is a y-intercept, right? Because its value of x is 0. But remember, they're intersections, okay? So that's right there how you use substitution and elimination on a system of nonlinear equations, okay, to find your solutions. Thank you guys. Let me know if you have any questions.